All right, let's start. Okay, so today we study this 1.7 chapter 1.7 about this linear independence. Okay, so let me start with the formal definition of this linear independence. So if you remember the vector equation form of our linear system, and then it can be the left hand side of our vector equation can be represented as these linear combinations of the given vector starting from v1 through vp, and then we have some unknown linear combination coefficient, right? And then in this case we consider the zero vector as a right hand side vector. Okay, so what was it called, especially in this case when we have zero vector on the right hand side? So it was called homogeneous linear system, right? Yeah, and then this linear system always had a solution, right? So yeah, we have three different cases in terms of the number of solutions, right? No solution at all, and a single or one solution, and infinitely many solutions. And in this case, this zero vector is always inside of the span of v1 through vp, right? So zero vector is always inside of this span because we can simply set these linear combination coefficient of any of zero for any vector that we are given here, and then we can easily create the zero vector, right? And so yeah, in this case, since the solution is always existing, so we always have at least one solution, and then there are two possible cases of having a unique solution or one solution only, and infinitely many solutions, right? So when we have infinitely many solutions for this kind of equation of this homogeneous linear system, and then in that case, those vectors of v1 through vp are called linearly dependent. Okay, linearly dependent. So that is the formal definition. So in other words, this homogeneous linear system has infinitely many solutions, and then these given vector starting from v1 through vp are called linearly dependent. And otherwise, if we have only one solution for this homogeneous linear system, and then these vectors are called linearly independent. Okay, and then if they are linearly dependent according to this definition, and then it means we always have a solution as all zeros. So that is one particular solution, and this solution was also, had also a special name of trivial solution, right? Because it's really trivial to obtain, because we can simply set all the variables of x1 through xp as 0, and thus that is called a trivial solution. And in other words, on the other hand, we can also think about this non-trivial solution, and that means among those coefficients, at least one of them is not 0. Okay, so at least one of them has some value other than 0. Okay, so if we can find at least one such solution, and then that's called this non-trivial solution, and in that case those vectors are linearly dependent. Okay, So that is the formal definition of this linearly independent or dependent. Okay, and then when we have, let's look at when we have non-trivial solutions or infinitely many number of solutions for this homogeneous linear system. So in conclusion, let me give just a simple answer about when we have an infinitely many solution in this case, or in other words, when we have a non-trivial solution. And that is actually the same as the situation where we have free variable. Okay, so your linear system has a free variable, and then it means your column vectors that are given are linearly dependent. Okay, so yeah, but on the other hand, if you don't have any free variable, that means all your variables are basic variables. Okay, in that case, your column vectors, your given column vectors are linearly independent. Okay, so that is a short answer, and let's see why. And also, we can think or understand this linear dependence from another perspective, and then I will describe it in a few slides. Okay, so let's look at this example. So we are given these three vectors, and then we have to determine whether they are linearly independent or dependent. Okay, and then if they are linearly dependent, and then the second problem is to obtain the actual non-trivial solution. Okay, so if they are linearly dependent, and then this homogeneous linear system will have a non-trivial solution that has non-zero at least for one of these variables that we have, and in that case, we want to find particular non-trivial solution that satisfies this. Okay, and then let's look at how it is related to the existence of the free variable. Okay, so if we have free variables, then those vectors are linearly dependent, and let's see why. So we first, the starting point is, so these three given vectors, okay, and then we just set this homogeneous linear system by just setting this b part as 0. Okay, and then the next thing to do is just the typical row reduction on this matrix, and then we will have this echelon form, and then maybe this one is our reduced echelon form, right? Okay, and then we have a pivot and pivots here, and no pivots on the third column, right? And so this is a basic, and this is a free variable, right? So far so good, right? And then we will just write our solutions so that we have a free variable, we have a basic variables on the left, and then free variables on the right. And then we also have this free variable explicitly for x3. Okay, in this case, let's just set x3 as 1, for example, or in this case, let's set x3 as 5. Then what will be x1 and x2? x1 will be 10, x2 will be -5, right? So in this case, simply because we have a free variable that we can freely set the value of, and then we can of course set that free variable as non-zero value. Okay, that non-zero value, one of the non-zero value was 5. Of course, it can be like 1 or -1 or maybe 2, 3, and so on. But let's just choose one of them. Okay, and then suppose that was 5, and then x1 and x2 are having these values, right? So in this case, yes, because we can choose non-zero values for our free variable. Yeah, this, yeah, accordingly, the other variables like x2 and x2, x1 and x2 are set, yeah, based on this particular free variable or non-zero free variable value, and thus we can, yeah, we found that at least one non-zero solution or non-trivial solution that satisfies our equation, right? Okay, so yeah, so we can satisfy the requirement for linear dependence relationship, right? And so based on our yeah, formal definition of a linear dependence, we can see that free variable allows us to give a non-trivial solution, and thus those three given column vectors that we started from, okay, so these are linearly dependent, okay? And then, yeah, we had this second question of finding the linear dependence relationship. So that is just simply writing out our solution in this form. Okay, so what does this equation mean? So we had a solution of, yeah, we started from this free variable, and by setting it as just non-zero value, and then accordingly we were able to determine x1 and x2, and then let's just plug these values into our equation over here. Okay, so we initially started from this vector equation by setting the right hand side as 0, right? And then x1 was 10 and x2 was -5 and then 5, I think, right? And then we can write it, let's see. Yeah, we can write it as 10v1 and negative minus 5v2 and 5v3 equals 0. Okay, so that way, yeah, we can find non-zero solution that satisfies this homogeneous linear system. So I just plug that in, and then you can just verify by just multiplying these, and then see if they are equal to 0 for the first element and the second element, and so on, right? Okay. And then can we find some other non-trivial solution? Okay, so we found one particular non-trivial solution, but in terms of the number of solutions, so we should have an infinitely many solution in this case, because we always, yeah, we can see that all zeros are our one solution, and then we found another solution here, and then yeah, there is no cases like having only two solutions in the linear system, right? So we can either have a, yeah, if we have a solution, and then we will have a unique solution, or I mean one solution, or infinitely many solution. And then we only found the second solution, and then, yeah, can we find any other relationship? Yeah, of course, by setting it as 1 or any other values, we can find some other solutions. Yeah, basically with the infinite number of possible solutions, right? Okay, so yeah, so far so good. Okay, and then let me jump to like this slide. Okay, let's see. Let me see. Okay, so let's now discuss about its practical meaning, or a little bit more intuitive meaning about it. Okay, so let's go back to this particular solution, like 10, -5, and 5. And then let's just try to represent this solution in this form. So 5v1, v3 equals -10v1 plus 5v2. Okay, and then v3 will be equal to -2v1 plus v2, right? So if we have this non-trivial solution, and then we can obtain this this particular form where we represented one of our given vector v3, okay, as a linear combination of the previous vectors, right? So this equation, you can understand this equation as v3 represented as the linear combination of v1 and v2, and of course the linear combination coefficient will be -1 and 1, right? Okay, so based on this observation, let's try to let's think about this this scenario where we have add our vector one by one and then consider their span. Okay, and then let's start with the first vector. So suppose this vector is a v1, and then what is the span of it? It will be just a single line like this, right? And then let's think about the second vector. Okay, and then the second, suppose the second vector was not along the line of this first vector. Okay, just like this case. Okay, in this case, because this second vector is outside of the span of the first vector, it actually increased our span from just a single very thin line into this plane, right? But let's look at the situation where we add the third vector. Let's try to add the third vector. But if our third vector is something like this, which means we have this kind of plane, right? This kind of plane, but this third vector is actually outside of our span of the previous vectors, right? So in that case, this third vector will actually increase our span, I mean the volume of our span, right? But if that particular equation is satisfied, which means the third vector is actually represented as a linear combination of the first two vectors, and it means this particular vector is not outside of the span, but it's actually inside of the span of these two vectors. So this first and the second, but the third vector was actually inside of our plane that is spanned by v1 and v2. Okay, so so that equation means when adding the third vector, it doesn't actually increase your span because the third vector is unfortunately it's actually inside of the span of the previous vector. Or the third vector can, if the third vector can be represented as a linear combination of the previous vector, and that means the third vector is belonging to the span of the first two vectors, and that's when this third vector doesn't increase our span into like a larger volume. So the span of these three vectors will be just the same as the span of these two vectors, right? Okay, so as you add one vector at a time, starting from the very first vector and then adding the second and third vectors and one by one, and then if you find at least one such vector that is represented as a linear combination of the previous vectors, like this kind of case, right? And in that case, if you can find at least one such vector as you add these vectors one by one, and then that's when you have this kind of representation, right? And this V3 is represented as a linear combination of the previous two, and then you can always represent it as this relationship or this kind of equation where we have some non-zero values as a coefficient, and then having a zero vector on the right hand side, which is our homogeneous linear system, and then suddenly it will give at least one particular non-trivial solution. Okay. Okay, and as I mentioned earlier, this linear dependence relationship is actually the same as the situation where we have a free variable, okay, and then let me explain, or let me say that this third vector, okay, so the third vector, which is already inside of the span of the previous vector, so this third vector is actually your free variable, okay, your free variable. So okay, so in this case our third vector is corresponding to this third variable, and this third variable didn't have any pivots on this column, right? So yeah, this third vector in this case is actually corresponding to our free variable, okay? And let's think about like this case where we have a pivot here, and then this is a basic and basic and basic, and this is free variable, maybe two of other free variable like here, which is our non-zero values, but it didn't actually have any pivots on this case. And then maybe another free variable here, okay? So in this case, how many variables do we have? Yeah, so suppose this is our staircase shape in our echelon form or reduced echelon form. So in this case, yeah, so we have quite many variables. 1, 2, 3, 4, 5, 6, 7. We have a 7 variable, right? And then we have 3 free variable and 4 3 basic variable and 4 free variable in this case, right? And in this particular case, if you think about this scenario where you add one vector at a time and then try to increase your span of these vectors, and then the first vector is like this, but what about adding the second vector? This second vector is our free variable, so that actually doesn't increase your span. That means the second variable is actually belonging to the span of the previous variable, and the previous variable was just single vector, and this second vector is actually belonging to this inside of this belonging to the span of the first variable. Okay, so the second variable doesn't increase your span, and then the third vector will actually increase your span like this. So first and the second and the third, okay, and then fourth one and fifth one will be something like this. So they are all inside of this span of these two vectors. Okay. Okay, so let me explain why this is true. Okay, so I just explained this situation without giving kind of why it should be true. Okay. So in this case, let's think about this homogeneous linear system by just setting the right hand side vector as 0, and then let's think of this as a reduced echelon form. Then it will be all ones, right? And then here we have all zeros, right? And 0, 0, and 0, 0, and 0, and 0, right? So this is our reduced echelon form. And then what about the value like here in the place of this star mark? That can be any non-zero value, right? Because that is not our leading entry, right? And so let's just set it as maybe -2 and maybe 3 and maybe -0.5, for example. Okay, so in this case, so I mentioned that, or I said that this second vector is actually belong to or that is inside of the span of the previous vector, which is v1, right? So we have v1 and v2, and then when adding v2 into our span, it doesn't increase our span, and thus it is like this kind of situation. So the second vector is along the along the line spanned by the first vector, and then in that case, what does that mean? v2 should be represented as the linear combination of v1, right? And what does that mean? So it is something like this, right? Some scalar value times v1, right? And then from this reduced echelon form, let's try to find this kind of solution. Okay, so in this case, so let's set this value as c. Okay, and then in that case, let's move this guy into the left hand side. Okay, so here what we are trying to do is, so let's try to start from this equation. Okay, this equation, and then let's try to change it into this form, which will give us the one solution or one non-trivial solution for our homogeneous linear system. Okay, so again, from this representation, okay, which represents a third vector or one vector that we try to add into our span, I mean, we can represent it, if we can represent it as a linear combination of the previous vector, and then by just moving all the right hand side vectors into the left hand side, and then we will obtain this kind of representation, and then that will give us the non-trivial solution for our homogeneous linear system, right? And then in this particular case, let's try to obtain what this c value is in this case. So let's try to move to the right hand side, and then it will be like negative c times v1 plus v2 equals 0, right? And then just let's rewrite it into this form, v3 and v7, for example, because we have a 7 variables in this case. And then let's just set all these values as 0 for the rest of the variables, and then this will give us this kind of representation, right? Okay, and then let's try to find what this negative c here. Okay, and for this v2, we are setting the linear combination coefficient for v2 as 1 here. Okay, so in this case, given this big reduced echelon form, let's just try to think about the vector equation form by just multiplying their linear combination coefficient. So linear combination coefficient like c, and what is the linear combination coefficient here? It is 1 here, right? It is 1. And all the others are set as zeros, right? So 5 more zeros over here. Okay, and then what will we see? Can you find the value of c from this reduced echelon form? So remember, I mean, let's try to think about it. Think about this equation as a vector equation. So it means we have this vector, right? And then we have this vector, and then for the other vectors, like all the way through the last column, I mean the last variable, and then they are set as zeros, right? And so we can just ignore these 5 other variables, and then let's just focus on these 2 vectors. And then again, the first vector was what? It's this guy, which is our pivot column, right? So this is our first vector. And then what is the second vector? So here in this case, it's negative 2 and 0 and 0, right? So can you make their linear combination to be 0? When setting 1 here, right, we have to find c here, or negative c here, right? So what will be negative c here? it will be just, so in this part, if it is a -2, and then yeah, we can just simply multiply it so that we can cancel this value out, right? So in this case, yeah, so by setting C here as, for example, 2 in this case, we can represent V2 as a linear combination of V1, right? Okay, and then in the case of a basic variable, this one will not be possible. And why? Yeah, let's understand why this will not be possible. Okay, so let's look at the third vector, and let's just try to set the rest of these vector linear combination coefficients still as 0. And so let's just try to ignore from V4 through V7. So we just ignore these later vectors because we didn't add these vectors yet. Okay, so we have currently V1 and V2 and V3, and then now let's try to represent V3 as a linear combination of V1 or V2. Okay, so in this case, because this one is a basic variable, it will not be inside of the span of the previous vectors, which means, so far we had a one vector, and the second vector was belongs to the span of the previous vector, and then the third vector is, because it's a basic variable, it will be outside of this line, right? So it's not belonging to the span of this first one, and then in that case, we should not be able to find this linear combination relationship. So yeah, we shouldn't be able to represent V3 as a linear combination of the previous vectors. Okay, and why it is not possible? So let's try to understand it. So the first vector was this guy, and then the second vector is this guy, which is belonging to the span of the first vector, and then so now here let's call this as C1 and C2, and then this one will be negative C1 and minus C2, and here 1 times V3, right? V3 is what? This guy. V3 had a pivot on its own column, right? And then it will be 0 and 0. Oops, yeah. So here we should have only one entry here, because this third variable will have the next pivot, right? Okay, so this one will be 1, which is our pivot that is contained in our third column, and then we will have all zeros. Okay, and then let's think about this representation. So can we find the C1 and C2 that satisfies this equation? Is it possible? It is actually not. It is because we have a pivot here, right? And then since we set the V3 as 1, and okay, so where does this 1 come from? It was coming from this representation when we try to represent V3 as a linear combination of the previous vector, and then this guy will have the linear combination coefficient as 1, right? So this one cannot be 0. So this one should be non-zero value, because that way we can represent it as a linear combination of the previous one, right? So this one shouldn't be 0, and thus let's set it as 1, and then this 1 comes to here, and then in that case, yeah, this 0 is actually this 0 column vector, right? And thus for each element, by just linearly combining those three vectors, we have to set them as 0, right? But in this case, we have non-zero here, right? Non-zero here. But what about these previous vectors? Because this is our pivot. Because this is our pivot. So in this case, this part, okay? This part will always be 0. Because by definition, this one is the leading entry in this row, and that means this one should be the first appearing one in that row, because that is the definition of the pivot or leading entry, right? Okay, so we have 1 here, and then we multiplied it by 1, and then we have to make it as 0 by just adding some other values. But in the previous vectors, those values are all set as zeros, and thus even if, I mean, whatever values that we multiply here, like maybe 5 and 4, yeah, they will still remain as 0, right? So in this case, we have no way to make the linear combination of the second row, okay, or second entry to be 0, right? So that way, this unique one in this pivot variable, by just involving the first, I mean the previous variable, and then this this variable or this vector that we are currently adding to our span, okay? So this 1 cannot be cancelled into 0 by using the previous vectors, and thus we cannot represent, yeah, or we shouldn't be able to find this representation that has 1 here, okay? So in this particular case, it should all be 0 by just using these 3 vectors, right? And that means we cannot obtain this linear combination relationship that represents V3 as V1 and V2 and yeah, these kind of previous vectors. Any questions about it? So, yeah, in summary, yeah, this one is actually showing that when adding your vector one at a time, okay, and then if the added vector is not belonging to the span of the previous vector, and then y, it should be a basic variable, and then in other cases where we have the third vector, which is belonging to the previous span of the previous vector, and then this one should be the free variable, and then this one shows the reason why this one should be a free variable, because if it is a basic variable, and then it will be the first one here in that row, because that is simply a leading entry. And then if we set the linear combination coefficient of this vector as maybe 1, and then there is no way to satisfy this homogeneous linear system. Or, yeah, again, if we set it as 1, and then this one will be 1, and then by using the previous vectors, because these values are all zeros, right? So these values are all zeros, so we cannot cancel out, or we cannot just make this non-zero value as 1 as a 0 value over here. Okay, so we cannot satisfy this equation by just setting the linear combination coefficient for our basic variable. Okay, so in that case, this basic variable or this column cannot be represented as the linear combination of the previous vectors, like these. Any questions about this? 네.
정리해가지고 얼리멘터리가 추가될 때마다 벡터 스팬 차원이 하나 증가한다고.
네. 네, 네, 맞아요. 그것도 네, 좋은 지적이에요. 네, 그게 맞는 말이고요. 그러니까 이게 그 피벗 있잖아요. 피벗이 있는 그 컬럼 있잖아요. 그 컬럼 벡터들, 우리가 지금 컬럼 벡터들을 하나씩 추가를 해가면서 우리의 스팬을 점차 이렇게 늘려간다고 생각을 하면, 그러면 베이직 베리어블, 그러니까 이렇게 베이직 베리어블이라는 건 뭐냐 하면 피벗이 있는 애들이에요. 피벗이 있는 애들은 이렇게 계단상으로 가다가 이렇게 뭔가 한 번씩 다 삐져나가는 애들이 피벗인 거잖아요. 그죠? 그 말은 아까 얘기했던 것처럼 지금 요 벡터는 이 그전 벡터들 이 두 개로 절대 나타낼 수가 없다는 거예요. 왜냐면 여기를 곱하기 1로 세팅을 해서 만들면 얘는 하여튼 1이죠. 그러니까 얘는 살아있는데 여기는 지금 다 0이니까 이 0을 아무리 합쳐서 뭔가 이 1을, 이게 우리는 이제 호모지니어스 리니어 시스템에서 여기를 0으로 만들고자 하는 거니까 이 0을 만들 수가 없어요. 그렇죠? 그 말은 여기 1을 세팅하면 이 방정식은 우리는 해가 없다는 뜻이에요. 그러니까 이 방정식을 만족시킬 수가 없어요. 즉 그 말은 이게 이 둘의 리니어 컴비네이션으로 표현될 수 없다라는 뜻이 되고요. 그 말은 첫 번째, 두 번째 추가했을 때 세 번째는 첫 번째, 두 번째의 스팬 혹은 첫 번째, 두 번째 리니어 컴비네이션으로 표현될 수가 없다라는 뜻이 돼요. 네. 그러면 또 이렇게 여기 네. 학생의 질문으로 돌아가서, 그러면 이 베이직 베리어블이라고 하는 거, 피벗이라고 하는 거는 항상 우리의 스팬의 차원을 늘려주느냐? 다시 한번 이야기하면 프리 베리어블은 그 해당 벡터가 추가될 때는 스팬이 안 늘어나고요. 그 다음에 거꾸로 베이직 베리어블은 스팬을 항상 늘려줘요. 항상 늘려줘요. 거꾸로 얘기해요. 즉 그 말은 걔는 앞에 것들의 리니어 콤비네이션을 표현이 될 수가 없다. 그 말은 스팬 안에 있지 않고 바깥에 항상 삐져나오게 된다. 또 그 말은 걔를 추가를 하면 우리의 스팬은 늘어난다 라는 뜻이죠. Okay, so let me briefly explain it in English as well about the student's question. So in the case of our basic variable and their corresponding columns will always increase our span, because that vector corresponding to our basic variable cannot be represented as a linear combination of the previous vector. And that means that vector is outside of the span of the previous vectors, right? And also that means when adding it into our span, I mean the ingredient vector that forms our span, and then it will always increase the volume of our span. Okay, and then related to this issue or this interesting characteristic, we can also think about the maximum number of maximum number of basic variables that we can have in a particular dimension. So let's just focus on our dimension as 3. So 3 by maybe 8. In that case, let's think about the homogeneous linear system, and then set the last column as 0, and then we have 7 different variables, right? And then here in this case, how many variables do we have in this case? How many pivots can we have maximally? So maximum number of pivots will be 3, right? And that means maximally how many basic variables do we have? Yeah, also 3. And then at least 4 of them, 4 out of 7 variables should be free variable. Okay, free variable. Okay, and then let's think about this case in terms of like adding our span. Okay, So these column vectors are living in this three-dimensional vector space, okay, three-dimensional like space. And then the first one, and then second one, and then the third one, right? Yeah, so maybe like in this case, BF, BF, F, B, and things like that. And what does that mean? The basic and then free variable is inside of our span, right? And then the next one is basic variable that actually adds or increase the span, right? And so far we formed this plane, right? This plane. So plane is yeah, we can think of this plane as two-dimensional kind of space, right? So yeah, so we have this case, and then the fourth and the fifth vector are all free variables, and they are belonging to these plane, right? And then now finally we have another basic variable, and I need more finger like this. Okay, so this is our 1, 2, 3, 4, 5, yeah, 6 variable. Okay, which is corresponding to this one. So in that case, previously we had this thin plane, and then we finally add the third one that is not belonging to this plane, right? And then adding this third vector, basic variable, and then what is our span? So span is now three-dimensional space, right? And then in that case, our span is actually the same as the entire space, right? Entire space. So again, our span is, yeah, the entire or the maximum possible space of this R3, and then the rest of the vectors should be always inside of the span of the previous vectors, because the span of the previous vector is literally the entire space, right? So there is no way escaping from that space, right? Because we are covering up the entire space. Okay, so so in that, yeah, by using this kind of understanding, we can also explain why we should have at least and most 3 pivots in this case. So we have a 3 rows, right? 3 rows, and thus the maximum number of pivots are 3 simply, right? But geometrically in this high dimensional space, we can we can also understand why it should have maximally like at most 3 basic variables. So basic variables are actually those vectors that that increases your span, right? And then you have up to 3 chances in 3-dimensional space, right? So that way you can have yeah, maximally or at most 3 basic variables in this case. Okay, and then also in this case, I think we discussed about this this case, but if we have a more variables than the number of dimensions, okay, again, yeah, so yeah, this is the number of variables that we have in current case, and then this is the dimension, right? And then if we have more number of variables, then we should have at least 1 free variable. So free variable will always exist, at least, yeah, at least 1 or more, right? So in that case, at some point, when adding these 7 vectors, 1 at a time, and then at least one of these vectors will be represented as the linear combination of the previous vectors, right? So in that case, they are always linearly dependent, right? Okay, so again, yeah, if we are given, or if we have more number of vectors than the number of dimensions, and then those vectors will always be linearly dependent, right? Okay, and then also you can, yeah, we can understand this situation from a slightly different angle. Okay, so when adding 1 vector at a time, And then, yeah, the question was, I mean, the situation that we are interested in was to like determine whether the current added vector are represented as a linear combination of the previous vectors or not, right? But let's go back to okay, and then let's just use one more example here. And then suppose we want to add the fourth vector here in this case. And then what will be the solution? At least, what will be one of our solution? So we can set it as 1, okay? And then we try to represent it as the linear combination of the previous vector. And then let's suppose this value was maybe 4. So this can be non-zero value, right? Because that is not a leading entry, and this column doesn't have any pivots, right? And so it can be non-zero value. Okay, and then we have to make this. We have to make or cancel this vector out into 0 vector. So we have to make this vector into a 0 vector. And then how can we manipulate the previous vectors so that we can cancel out that vector? So we have 4 here, right? 4 here. And then we have 1 here, which has our pivot, right? And that pivot column will have only non-zero entry over there, but all the other entries as 0, right? And then in order to represent this guy, we can make it by multiplying by -4, right? And then we can cancel this out, right, by using this pivot. And then for this 3, how can we cancel it out? So we're going to use this pivot, right? So pivot, this value of 1 will always exist because that is our pivot variable, and this one is not our pivot variable. That means even if this value is not 0, we can always find the previous vector that has this value as 1, right? Because the pivot should be the first appearing non-zero entry in that row. Okay, so how can we cancel out this value of 3? We can just simply multiply -3 here in this case, right? And then what about the second variable? We don't actually need to use it, right? So we can just simply set the linear combination of that second vector as 0. Okay, so with 0 here, and then suddenly we obtain this -4 times v1, and then 0 times v2 plus minus 3 times v3 plus v4 equals 0, right? So that was coming from our effort to try to represent this v4 as like 4v1 plus 3v3, right? Because we had again we have 4 here, and then we can create that 4 by just multiplying the first pivot, and then for this 3 we can make that 3 by just multiplying the second pivot by 3, right? So that way we can represent this guy, right? But let's now focus on this representation. Okay, this representation, which is our homogeneous linear system. Okay, so our definition of this linear dependent vectors, in this case, we should have the non-zero or non-trivial solution for this homogeneous linear system. And then let's try to understand this equation a little bit more. Okay. So in this case, we can understand this as a kind of a process of adding our vectors. Okay, adding our vectors. So let's start with the simple case of v1 plus v2. So we are just given 2 vectors, and then we just simply add them together. And then suppose our v1 is here, and this is our v2. And then what will be the resulting addition of the vectors as we studied this guy, right? So we form this parallelogram, and then we find out the vertex of the this parallelogram. So that is the resulting vector. And then we can also understand this process as follows. So we are kind of applying kind of sequential process of adding vectors. So v1 and v2, and then in that case, we first move from the origin to v1 here. So this is our destination in the middle of this addition. And then we set this as 0, and then move move to the new point by following the second vector, which means starting from this as the origin, and then we just go to this new point by just following v2. Okay, so yeah, this is another simple way of understanding this vector addition. And then of course v1, v2, and v3 can be like, suppose we have a v3 here, and then it's like here we are adding v3 here. So this is our final destination, right? So we can think of this vector addition as this sequential process, right? And then let's think about this case, right? And then so we are given vector v1, and then multiply it by -4, and then you know how to form the -4 times v1. So if v1 is here, and then we just reverse the direction, and then increase or extend the length of the vector by 4 times, right? And then that will be our first destination. And then the second destination, which is adding nothing here in this particular case, but here in this case, we also think of this -3 times v3, right? And then just starting from that point where we use this vector, and then we just start from there and then move to another point, and then move by following this another vector, right? So it's like moving, starting from origin from the very beginning, and then move to a new point, and another new point, and then another new point, and so on. And then what is our final destination? What is our final destination? It should be origin again. So it's like, so you're leaving home, and then went to somewhere else, and then stopped by at some of the different points, and then finally you have to go back home actually. So you have to go back to the very first point of our origin, right? So that is another kind of perspective of an understanding kind of linear dependence relationship. So again, from the definition of a linear independence will have the unique solution in our homogeneous linear system as all zeros. So in that case, v1 and 0 v2 and 0 v3 equals 0. So in that case, by just multiplying all zeros on our vectors, so we are not actually leaving our home or our origin. So we haven't moved at all, starting from our origin, right? But suppose one of them, okay? Suppose one of these linear combination coefficient was something like 1, which is non-zero value, okay? So in this case, at some point, you will actually leave the origin to some other points, right? But once you left your home to somewhere else, and arrived at somewhere else, and then by using all the rest of the vectors, right? And then using all the later vectors, you have to have a way to go back to your home, of an origin, right? Okay, so again, in the case of linear dependence relationship or linearly dependent vector, so suppose this one is origin, and then by using your vectors like v1 through v3, if they are given originally given vectors, and then v1 and v2, I'm just thinking of this multiple scalar multiple of our vectors, like some multiple of v1 and some multiple of v2 and then some multiple of v3 should bring you back to home, which is our origin. Okay. So in this particular case, so this one can also be thought of as having an infinitely many solution. I mean, the reason why we have to have an infinitely many solution. So suppose we have a v1 as 1, 2, 3, and then 4, 5, 6. And suppose we are given this vector equation like this, and then just so I'm gonna add another vector plus maybe something like this, and then what was the number? 6, 9, 12. Okay, so in this case, let's just try to find one of our solution. So in that case, I just had a solution already in mind. So I just put here 2 as 2 here and 1 here and 0 here. And then we can see that this one is one of our solutions that satisfies this equation, right? So what does that mean? What does that mean? So let's just think about this kind of process of sequentially moving to a new point and then another new point and so on. So in this case, starting from the origin here, and then so we had a vector v1, but we just use a scalar multiple of 2 times v1, and then maybe something like this as 1 times v2, and then no v3 was used here. And this is our destination, final destination, right? And then what should this final destination be? That should be 6, 9, 12, right? So we are now thinking about kind of a general linear system where we have a non-zero vector b here, and then that point should be our final destination, right? So that is one of our solution, 0, 2, 1, 0, or these 3 linear combination coefficients will bring you to this final destination as here, right? But let's think about its homogeneous version of the linear system. I mean, homogeneous linear system will be having the same vector, right? And then what about the right hand side? The right hand side will be just a simple all zeros, right? Simple vector of zeros, and then the same vector will be used here. Okay. Okay, then given this new linear system, and then suppose you found at least one way to satisfy this by using at least one non-zero among these 3 values. Okay, and that means we have 0 vector here, and that means in this case, so I also carefully manipulated in a way that -1, -1, and 1. So that will be one of our solution for homogeneous linear system, right? So you guys see that, easily that this one is true. And then what does that mean? So it is like, so looking at this equation, so we are origin here, and then we move to a new point by just multiplying v1 by -1, and then maybe -1 v2, and then 1 times v3, and then it should bring you back to home because our origin vector is given on the right hand side. right? Okay, and then let's compare, or let's utilize this kind of solution into this original linear system. Okay, so back to this original system. We arrived here properly into this final destination that we are given, and then we just apply this solution into here. What I mean by that is, let's start this point as our origin, okay? And then we just draw this kind of triangle like this and this and this, okay? So in that case, yeah, if you were able to come back to the origin point, and then starting from this point as a new origin, and then by just drawing the exact same triangle over here, and then you can always go back to the this original point, which was our solution. Is it right? Okay, and then so this one, yeah, from the sequential process, okay, 2, 1, 0 was our one of our solution, and then starting from there, we just add this vector, and this vector, okay. That is corresponding to like going, yes, leaving this point to a new point, and then new point, and then coming back to this original point, right? That will be our new solution as well, because that will also have the final destination of this point, okay. So that means 2 times v1, 1 times v2, and 0 times v3, and then plus. So we are doing the sequential kind of vector addition, and then do another set of a sequential vector addition like -1 times v1, -1 times v2, plus 1 times v3. That will give this exact same point, because these further movements will not change the original starting point, right? And then what does that mean? What does that mean? So this one will give us the same vector here, but we can think about the new linear combination of these three vectors. What is that linear combination? It will be 1 and 0 and 1, okay? So suddenly it gave a new solution, right? So initially or previously 2, 1, 0 was one of our solution, right? But if your three of your vectors are linearly dependent, and then from this linear homogeneous linear system, you should be able to find at least one non-trivial solution, and then by just applying that non-trivial solution in the context of this sequential movement of a vector addition, okay? And then this guy, from this figure, it will satisfy this, and thus it will give a new solution over here, okay? And suddenly we now have a two different solution that satisfies this original equation, right? So that way, if you have a linearly dependent relationship of your column vectors, and then the number of solutions will be infinitely many, okay? Because this non-trivial solution will always make this destination, will not change this destination, but just moving, to a kind of another point, and then coming back to the original point, okay? So linear dependence is actually the same as having the free variable, right? So this is what we understood from this echelon form pattern, right? And then linear dependence and also the free variable will give us infinitely many solutions for your linear system, okay? So that's how we can kind of relate various things that we learned in this class. But here, one necessary condition is also should be considered. So what if, so at least, in order to have an infinitely many solution, we at least have to verify that this vector B should be span, it's like, should belong to the span of our three vectors. In this case, V1, V2, and V3. Okay? So that is kind of necessary condition, or the first condition that you have to check whether you determine, before you determine whether you have a unique or infinitely many solution. Okay, we have to verify that the solution is actually existing. Okay, and also, in this case, it can be viewed as like the discussion that we used previously. So suppose this particular linearly dependent vectors like this. Okay, so we are living in these vectors are living in the three-dimensional space, but your three-dimensional vectors are something like this. So the first, second, and the third vector, and this third vector is actually belonging to the span of the previous two. Okay, and in this case, we have the span of these three vectors as this thin plane, and then if our B vector is outside of this span, and then we will not have a solution, right? But in case this guy is happening to belong or inside of the span of these three vectors, right? Three vectors, and that's when we have infinitely many solutions, right? So in that case, we cannot have a unique solution. So we should always have an infinitely many solution, and then the reason why can be explained by this kind of understanding, or it can be understood like, so we have three different vectors in our span, and that can be viewed as a kind of redundancy. Okay, redundancy. So for the same plane, right? Same plane, only these two can also span fully span this given plane, but we are adding this, we have another redundant or kind of superfluous vector over here. And then if we're given one point belonging to the span like here, and then we can have a infinitely many different ways of representing this point as like this parallelogram, or maybe this parallelogram, or maybe this parallelogram. Okay, so we have infinitely many different ways of representing that particular point by using these different shapes of our parallelogram. So that redundant vector or free variable will actually give this a redundant kind of representation, and that's why we have an infinitely many solution. Okay, so that is like kind of an intuitive understanding of linear independence and dependence. Okay. So I think that's it for today. So so let's see next week. Okay, thank you.
여기 그 리니어 매트릭스로 나타냈을 때 이거를 m으로 두고 해를 제어한 열을 n으로 두면 n이 n보다 클 때 항상 리니어리 디펜던트하다고. 근데 이게 일반적인 경우에서 이해가 되는데 맥락이 이제 만약에 좀 극단적인 경우 있잖아요. 예를 들어 피벗이 이제 4개 이상 있을 수 있다고 하셨는데
피벗이?
네, 피벗.
그래요? 여기서 보자. 여기서 피벗은 그러니까 리딩 엔트리가 많아봤자 3개이고, 그러니까 리딩 엔트리라는 게 이게 우리가 에슐론 폼에서 만든 이제 리딩 엔트리니까 에슐론 폼에서의 리딩 엔트리가 곧 이제 피벗이라고 불리잖아요. 그러니까 이제 피벗이 내가 이야기를 잘못했을지 모르겠는데요. 피벗은 여기서 이제 3개까지만 존재할 수 있어요.
아, 네. 용어를 잘못 썼어요.
아니 뭐 내가 이야기 잘못했을 수 있어요.
그 XXX 이런 식으로 리딩
그렇죠.
소리가 있으면
근데 이렇게 쪼로록 일지 아니면 이렇게 띄엄띄엄 일지. 그러니까
네.
쪼로록이면 지금 B, F 쭉. 그러니까 베이직. 그다음에 나머지가 다 프리 베리어블이라는 뜻이고 이렇게 띄엄띄엄 있으면 중간에 이제 프리 베리어블도 몇 개 껴 있고 그다음에 또 베이직 하나씩 나오고 뭐 이런 식으로.
네. 여기서 질문.
네.
그래서 이제 전체적인 오늘 수업 맥락이 여기서 그러면 여기 요런 값들 있잖아요.
네.
리딩 엔트리에 있는데 0이 아닐 수 있는 값들.
이게 일단은 요 리딩 엔트리 그러니까 피벗이 어딘가 이렇게 있어요.
네.
그럼 일단은 이제 우리가 리듀스 에슐런 폼을 따지면 이 지금 여기는 다 0이어야 돼요. 위아래로 우리가 다 없애주니까.
네.
근데 중요한 건 이제 이런 애들이죠. 이런 애들은 그리고 여기도 마찬가지고. 그러니까 여기는 0이어야 돼요. 이 피벗을 위아래로 쭉쭉 보면 다 0이어야 되는데 이 옆에는 지금 이런 애들은 0이 아닐 수 있죠.
네. 근데 0이 아닐 수도 있는데 0일 수 있는 0이 아닌 경우에는 이제 이게 다 전적으로 맞는데 0이 될 수도 있는 극단적인 경우로 리듀스드 에슐론 폼이 되기 전에
네.
이제 이 평행한 벡터 그러니까 같은 벡터라고 볼 수 있는 게 이렇게 늘어서면
네, 싹 다 0이 되는 경우.
네, 그러면 이제 이게 인디펜던트 하게 되니까
그 경우에 이게 만약에 이제 이쪽의 벡터가 이쪽에 하나가 싹 다 0이었어요. 이게 프리 베리어블인데 만약에 여기가 이렇게 뭔가 0으로 다 나타났어요.
네.
0으로 나타났어요. 이 경우도 그러니까 이게 좀 하나 스페셜 케이스가 있는데 0 벡터가 껴 있는 경우에는
네.
무조건 리니어리 디펜던트 해요.
0이 껴있으면 리니얼.
그게 왜냐하면 이제 0 벡터라는 거는 지금 뭐 첫 번째, 두 번째, 그 다음에 뭐 세 번째가 이렇게 딱 그 플레인 안에 쏙 들어가면
네.
이게 리니얼리 디펜던트한 경우잖아요. 근데 이 벡터가 아예 그냥 0이라는 원점이에요.
네.
원점은 그러니까 어떤 벡터들의 스팬에도 다 포함이 돼요. 왜냐하면 리니어 컴비네이션으로 그냥 0, 0 세팅해버리면 걔를 나타낼 수 있으니까. 그래서 이게 0 벡터가 끼어 들어가면 무조건 리니얼리 디펜던트 하고요. 그 다음에 그건 또 어떻게 볼 수가 있냐면 우리가 V1, 뭐 V2, V3 뭐 이렇게 쭉쭉 해갖고 이걸 0이라고 할 때
네.
여기에 이제 우리가 하나라도 난제로 값을 세팅해서 이 방정식을 만족시킬 수 있으면
네.
그러면 이거를 리니얼리 디펜던트하다라고 부르잖아요. 이게 우리가 처음에 배웠던 정의였잖아요. 그러니까 이게 뭐 예를 들어서 얘가 0벡터예요 무조건.
네.
그러면 거꾸로 얘를 만약 1로 세팅을 해요. 그 다음에 나머지 그냥 0으로 그냥 간단하게 세팅해요. 그 0벡터 곱하기 1은 여전히 0이고
네.
0벡터가 아닌 애들은 그냥 0으로 다 세팅해버리고 개수를. 그러면 이렇게 더하면 이거는 무조건 0벡터를 만들어낼 수가 있어요.
그런 경우에 인디펜던트 하지 않나요?
이거는 디펜던트하다라고 얘기해요. 왜 그러냐면 이 정의상 여기 보면 이제 여기를 난제로 값을 코에피션트를 난제로 값을 세팅을 할 수가 있는 거잖아요. 이 호모지니어스 리니어 시스템을 만족하도록.
그러니까 0이 아닌 다른 값이 오면 상수값에 0이 아닌 다른 값의 x1, x2, x3
네.
해상이 있으면 인디펜던트 하다 했는데
네.
0벡터인 경우에는 이게 상수값에 0벡터가 들어갔다고 볼 수도 있어서
네, 그렇죠. 상수 벡터는 거기에 난제로 값을 그러니까 0이 아닌 값을 곱해도 여전히 뭐 결과적으로 0벡터잖아요.
네.
그러니까 얘는 내가 자유롭게 세팅할 수가 있어요.
그런 식으로 생각해서 이제
네.
0벡터인 경우에는 상수값에 뭐 0이 아닌 게 와도
네, 그렇죠.
디펜던트한 경우로.
네. 그래서 이제 0벡터가 껴있다. 그러니까 벡터가 한 5개 주어져 있어서 얘네들이 리니얼리 인디펜던트하다, 디펜던트하다를 결정해야 될 때
네.
0벡터가 이 중에 하나라도 껴있다? 그러면 얘네들은 그냥 볼 것도 없이 리니얼리 디펜던트해요. 이거를 설명을 좀 아마 다음 시간에 조금 뭐 비슷한 얘기를 조금 더 할게요.
감사합니다.
문의사항에서
네.
두 가지 있는데 첫 번째가 이제 마지막에 말씀인 리던던트?
네.
그게 어떤 걸 의미하는 건지.
리던던트라는 건 이제 주어진 어떤 평면이 있을 때
네.
평면이 그러니까 이 두 개만의 벡터로 충분히 다 스팬이 되는데
그렇죠.
근데 여기에 하나가 더 껴 있어요. 스팬을
네.
하는데. 예. 그러면 한 포인트를 우리가 평행사변을 만들 때 딱 두 개. 그러니까 리던던시 그러니까 중복이 없는 상황에서는 포인트가 하나 딱 주어지면 이 주어진 두 개 벡터, 그러니까 이 평면을 스팬하는 이 두 개 벡터로 얘 포인트를 만들 수 있는 그 평행사변형은
네네.
그 평행사변형의 모양은 유일하게 하나예요.
네네. 그렇죠.
근데 우리가 지금 벡터를 필요 이상으로 지금 3개가 주어져서
예.
얘 하나 포인트를 만들어낸다는 말은 이 세 개의 어찌됐건 적당한 합으로 얘를 만들어내면 되는데,
그죠.
네. 그러면 이 두 개를 가지고 얘도 만들어낼 수 있고, 이 두 개를 가지고도 얘를 만들어낼 수 있고, 또 이 두 개를 가지고도 또 얘를 만들어낼 수가 있다는 뜻이에요.
네네.
그 말은 결국은 이 평행사 변형을 만드는 굉장히 다양한 방법이 있다. 그리고 그 평행사 변형을 만든다라는 게 뭐냐? 그 평행사 변형을 만들기 위해서 각각의 그 저기 벡터에다가 길이를 몇 배를 해줬느냐? 그 몇 배라는 게 우리가 지금 찾아야 되는 그 솔루션이잖아요. 그렇죠?
그렇다면은 리던던트라는 표현은 뭐 어떤 방식으로, 그러니까 표현을 어떻게 하는 거죠? 그러니까 세 개의 벡터가 리던던트하다 뭐 이런 식으로 표현하나요?
그러니까 결국은 linearly dependent한 벡터들은
예.
그냥 이게 그러니까 수학적으로 어떤 공식적인 용어는 아니고요.
네네.
그냥 그 직관적으로 생각할 때
직관적으로.
네, 리던던트라는 뭐 수학적인 용어는 뭐 따로 없고 그냥 내가
예.
설명하기에 좀 직관적으로 좀 이해할
알겠습니다.
만한.
감사합니다. 그리고 다른 게 저번에 또 제가 이제 퀴즈가 제출 제대로 됐는지 해서
네.
이메일을 제가 오늘 아침에 보냈는데.
아 그랬어요?
네.
그 내가 확인을 그러면 해보고
예,
다시
예.
알려줄게. 나한테
알겠습니다.
보냈나요? 아니면 우리 조교한테?
교수님한테 직접
알았어요.
보냈습니다.
그리고 지난번에 몇 명 학생들이 그거 저기 확인해달라고 했는데 뭐 다행히 그 친구들은 잘 등록이 된 것 같아서
네네.
크게 뭐 문제가 없지 않았을까 싶은데 난 다시 확인해보고
예, 예.
내가 이상이 하여튼 내가 알려줄게요. 다시.
알겠습니다.
교수님 지난 시간에 제가 몸이 안 좋아서 못 나왔어요. 그래서 그날 교수님께 메일을 보내드렸는데
이거를
공식적인 메디컬
네,
토크 같은 게 있습니다.
그런데 어떻게 처리를 해야 될지 좀 모르겠는데 그 한번 내가 좀 방안을 다시
연
생각을
부채
해보고
과세라던가 그런 거 있으면
그래서 내가 다시 좀 생각해보고 다시 알려줄게요.
알겠습니다.
네.
돌아보겠습니다.
네, 그래요. 네.